an ANOVA. So, how do you test when you have differences between groups? When you have simply two groups, you can just do a t-test. Remember, a t-test looks at the differences between just two groups. But what happens if you have more than two groups? So you have three groups or four groups. What do? Do you run a bunch of t-tests comparing each of the different groups? So for example here, we have caffeine, the effects of caffeine on heart rate, right? So we have participants who got no caffeine, those who got 100 milligrams of caffeine, and those who got 200 milligrams of caffeine. And as you can see, the more caffeine people consumed, the faster their heart rate. So if we were going to just do comparisons using t-tests, we can compare no caffeine to 100 milligrams, 100 milligrams to 200 milligrams, and then no milligrams to 200 milligrams. So we have to run three different t-tests to get a sense of what's happening. That's a problem. The question is why shouldn't we do this? We could do it, but there's a problem here. So what I want you to recognize is that the more comparisons that you test, the more likely you are to have inevitably get a type 1 error. So let's look at this example here. So if we have two means, we just have one comparison. So our probability of making a type 1 error is going to be 0.05, because we set it to be 0.05. If we now have three means, we have to do three comparisons. So like back to our caffeine example. Now our chance of making a type 1 error has increased to 14%. And now let's say if we had 20 a 3 by 3 by 3 design, which would give us 27 means to deal with, we'd have 351 possible comparisons, and there's almost 100% chance that in one of those we would make a type 1 error. So once you get beyond, I'd say, two or three groups, you're gonna want to avoid doing t-tests, because t-tests are really just about two. If you have 4, 5, 6 groups, you're going to increase your chance of making that type 1 error. So what an ANOVA does is enables us to look at differences between three or more groups, but without ultimately increasing our type 1 error. And to be clear, an ANOVA also can just run analyses if you have two conditions. It does two or more, but typically if you only have two, people do a t-test. If you have three or more, you would run an ANOVA. And the basic concept of a t-test and ANOVA they're very similar. So looking at between group variability and within group variability for both. So analysis of variance compares the amount of variability that is due to systematic changes in the independent variable. So like our t-test, that's the differences between our groups, so the mean differences between your groups, and comparing that to the variance that's due to random error. So that's our within group variability. And you can think of it like random error is any variability that you can't attribute to the independent variable. It gets attributed to random error. And that could just be any type of error that might be involved in terms of measurement error, participants weren't paying attention, individual differences in people's abilities. All that is considered random error. So what you have is the variability that's due to differences between the groups, which is your between group variance. And then you have variability that's due to random error, and that is our within group variance. So what does an ANOVA tell us? It's trying to tell us if at least one of your three groups, if you have three, say you have three groups, if one of those three groups differs from the others. So however many groups you have in your analysis, it's trying to determine if at least one of them is different from the other. So the null hypothesis for the ANOVA is that the means for all of your groups are exactly the same. So if you have three groups, the mean for group 1 is the same as the mean for group 2, which is the same as the mean for group 3. The alternative hypothesis is that at least one of those means is different than the others. Now, an ANOVA is what's called an omnibus test, meaning that it can tell you that one of the groups is different, but it can't specifically tell you which one is different. We have to do additional analyses to be able to figure that out. But the goal here is for an ANOVA is to tell you, wait a minute now, one of these groups is significantly different than the others. It could be all of them are different, but at minimum, one is different. So let's go back to our caffeine example. If we're trying to deal with between group variance, that is the variability or the differences between our groups. Within group variance is how much variability there is around the means for our groups. These lines here are called error bars. They give you a sense of the amount of variability around your means. The smaller the error bar, the less variability. The larger the error bar, the greater the variability. So an F statistic, just like a T statistic, is creating a ratio between these two variances. So between group variance, within group variance. So just like a t-test, you have between group variance over within group variance. You're going to get that ratio. And again, the between group variance is the differences between your means. The within group variance is the variability of your scores around those means. And just like a t-test, you can increase an F ratio, it's like a t ratio, by either increasing the between group variance or by decreasing the within group variance. So it's a ratio. So you can just basically have the differences between the means larger, or you could try to get the variability around those means to be smaller. Either of those approaches is going to make that ratio bigger. Larger F statistics or F ratios equate to more likely to have a statistically significant result, just like with a t-test. So for this example here, we have a lot of variability around our means because, again, this error bar is really big. So we're going to ultimately get a very small F ratio, right? So because there's so much variability around the means and there's not as much variability between the means. Now, if we reduce the variability around the means, even if we kept the between group variance the same, we're going to get a much bigger F ratio because now we've minimized the variability around our means. So again, what I want you to walk away with is you want to have a lot of between group variance and less within group variance. So the more variability that you can attribute to the differences between your means, which is your between group variance, the better. You want the majority of the variability on the dependent variable to be due to differences between your groups than variability around the groups. And with samples above 60 people, an F greater than 3 is likely to be statistically significant. So I'm more of a visual person, so I'm going to give this to you visually. So imagine this pie chart represents all the variability on the dependent variable, right? What ANOVA is trying to do is trying to calculate how much of that variability can we attribute to the independent variable and how much should be attributed to random error. So as you can see here with this particular pie chart, the majority of the variability on the dependent variable is due to random error or within group variance. And a much smaller portion is due to between group variance or the effects of the independent variable. So this would be a situation where you most likely would not have a significant effect of the independent variable because not that much variability on the dependent variables due to the manipulation of the independent variable, that section in blue. Here now, this particular pie chart is indicating that there's an equal amount of variability between the independent and dependent variable. So here, half the variability is due to the independent variable, half is due to random error. So if we calculated this F statistic from this ratio, we get an F of 1. This third one here now, there's much more of the variability due to the independent variable than due to random error. This is the scenario where you're going to have a statistically significant result because it's saying that of the variability on the dependent variable, much more of it is due to the independent variable than is due to random error. So here is what an F distribution looks like. Don't worry yourself about it too much, but what I want you to recognize here is as you get F values that approach 3, you're going to likely have a statistically significant result. So if you have at least 60 people, an F value of 3 is going to give you a statistically significant result. So that means that ratio is going to have to be 3 to 1 um, for you to be able to reject the null hypothesis. And I want you to recognize this F distribution is not normally distributed. It is definitely skewed, but as you get to an F of 3, it's going to be statistically significant with 60 or more people. As you have more people, um, you can have a lower F value and still get statistical significance. All right, so we've touched upon this a little bit, but I'm going to come back to it now and flesh it out in more detail. So one way in which you can get a larger F value is by decreasing within group variance, right? So making the variability around the mean smaller. And you can do this methodologically by making sure that your sample is relatively homogeneous, right? So the more similar the people are in your sample, the less variability there's going to be between people. So you don't want to give people a test and some of them are like eighth graders and some of them are second graders and some of them are college students, because you're going to get a lot of variability in people's ability. What you want to get is a sample of people who have relatively the same level of ability, and that will reduce your within group variance. Also, having very good independent and dependent variables will reduce some of this within group variance as well, because if it's very clear, people will respond to it and understand it and give you similar responses. When you have a bad independent or dependent variable, it's vague and people respond to it differently or interpret it differently. That just ultimately leads to random error. You want to have everyone have the same experience in regards to the independent variable and interpret and understand the dependent variable in the exact same way so that you minimize unnecessary variability between people. The other way that you can get a larger F value is by increasing the between group variance. And the main way to do this is to ensure that your manipulation is very strong. So we talked about strong versus weak manipulations a couple of classes ago. A strong manipulation is where the differences between the level of independent variable are very drastic, right? So going back to our example from before, if you give people negative feedback, you could say like in one condition they say, look, you scored in the top 90th percentile, and in the other you scored in the bottom 10th percentile, right? Those are very different situations versus if you told one group they scored in the 51st percentile and the other group the 49th percentile. That difference is not going to be as drastic. You want to have stronger manipulations where the difference between the levels of the independent variable are very drastic. By doing that, you're going to essentially give yourself the best chance of getting a large between group variance. All right, so let's quickly talk about the number of F statistics that you can have. So an ANOVA will calculate an F statistic for every main effect and every interaction. Okay. So if we have a 2 by 2 factorial design, how many F statistics will an ANOVA produce? If you think it through, it'll give you 3 F statistics. One for the first possible main effect of the first independent variable, another for the possible main effect of the second independent variable, and a third for the possible interaction between those two independent variables. So if you run a 2 by 2 ANOVA, you will receive 3 F values, F statistics, to try to interpret. So what an ANOVA is going to do, it's going to partition out the variability on the dependent variable to either the first independent variable, the second independent variable, the interaction between those two variables, and random error. And it's going to essentially look at the variability that's due to the first independent variable in comparison to random error, the second independent variable in comparison to random error, and then the interaction in comparison to random error. So you're always forming a ratio, and the random error is always the same for all of these particular ratios.